Hello everyone, my name is Smit Baua. I am an application engineer for electromagnetics with Altair. In this video, we will perform steady-state thermal analysis of an antenna using Altair Feko and Altair Optistruct. The workflow that can be followed to perform thermal analysis involves three major steps. The first step involves creating a Feko finite element model of the device of interest. Feko will export per element loss information to a EPL file that can be used. The second step is to create a new Nastran file using a Altair compose script which can be used with Optistruct. The third and final major step is to set up and perform thermal analysis in Altair Optistruct. To demonstrate the above workflow, let's take an example of a patch antenna. We have set up the model in Feko. The geometry is a rectangular patch antenna that is enclosed in an airbox. The dielectric materials for substrate and air are defined in the project file. We will use copper for all the metallic faces that include the radiating patch and the ground plane. The thickness of the copper material is set to 35 micrometers as shown. We shall use the finite element method in Feko to solve this entire simulation. Under solver settings, check the option to export the material losses in the mapped heat loads file. Next, we decouple the method of moment solution and use absorbing boundary condition to conduct pure FEM analysis. We set the frequency to 2.93 GHz. We set the incident power to 30 watts, which means that the antenna would push 30 watts of power. Once we set up the geometry and the solution settings, we can go to the mesh tab and create a fine mesh. Once the mesh is generated, we can go to the solve run tab and run the Feko solver and wait for the solution to complete. You can observe different solution stages. Once the simulation is complete, we can press the green OK button. Once the simulation is complete, the required material losses and mapped heat loads are exported to a file into the directory where the Feko model is saved. To convert the mapped heat loads in OptiStruct readable format, we run a compose script. Open map.oml in Altair Compose. In Compose, set the work directory to this directory with the scripts. You can find the file browser on the upper right corner. Run the map.oml file. Select the total of 3 files when prompted and specify a name for a new output Nastran file. The script writes a new Nastran file. This file includes lines that point to FEM files, one per frequency point, that contain the electromagnetic losses, that is the heat loads. You can find the new Nastran file that will be extracted to the directory of the model. The next step is to set up the inputs for thermal analysis in Optistruct. Once we open HyperMesh X, we make sure that the solver interface is set to Optistruct. In the next step, we import the solver deck. Navigate to the new Nastran file that was written by the compose script and click Open. Then click on the Import button. Close the message window as the errors may refer to elements of air that are currently not needed. In the next step, we save the file and give it an appropriate name. There are different options at the bottom of the user interface to change the type of view and different ways a user would like to observe the model. By opening the Components section in the model browser, users can observe all the different regions and faces that are imported. One component is the outer air object. Select the component, right-click and delete it. The effect of air will be represented by convection boundary conditions on other components. Finally, give all the other components appropriate names like copper, substrate, and ground plane, and choose an appropriate color. In this step, we will define the different materials and their properties that are required for thermal analysis. Right-click in the model browser and select Create. Click on Material from the available options. In the Entity Editor, provide a name FR4 and change the card image from Mat1 to Mat4. Also provide an appropriate color for the material. Specify the thermal properties of the material as shown. You see that the FR4 is now defined under the Materials section. With the help of similar steps, create a material copper with a much higher thermal conductivity as shown. Once both these materials are defined, under the Materials section in the Model browser, we see both the materials that we just defined. The materials defined cannot be assigned to the components directly. For this purpose, we define a 2D or 3D material property. Right-click on the Model browser and click on Create. Select Property from the available options. In the Entity Editor, name the new property as Bulk FR4. Change the card image from P Shell to P Solid. Click on Unspecified next to Material and choose FR4. Select an appropriate color and click on Close to define the material property. Under the Properties section in Model Browser, you should see a new material property defined with the name Bulk FR4. The properties of this Bulk FR4 can be accessed by accessing the Entity Editor at the bottom of the user interface. To define the material property for copper, once again, right-click in the Model browser and choose Create and then select Property. In the Entity Editor, name the new property as Sheet Copper. Leave the new property or the card image to P Shell, as copper elements are 2D elements. Next, specify the thickness as 35 micrometers. Select an appropriate color and click on Close to finally define the property. Once again, you should see sheet copper that is defined, and by clicking on it, you can access the properties of that material. Remove all the undefined properties that you see by right-clicking on them and clicking on Delete. Once this is done, you can finally save the model. In this step, we will assign the material properties that we defined in the previous step to different components. Under the Model browser, open the Components section and select any particular component. Click on the property in the Entity Editor at the bottom and choose the appropriate property. Repeat these steps for all other components. We assign the property of sheet copper to both patch and the ground, and we assign bulk FR4 to substrate. The model browser shows two load collectors per Feko frequency, one for the volume losses in the dielectric and one for the surface losses on the metals. Optistruct accepts one heat load per simulation, so the two have to be combined. This can be achieved by load add. Right-click in the model browser and select Create, then click on Load Collector. In the Entity Editor, select an appropriate name. choose Load Add from the card image. Next, to load numerical set, specify 2 and then click Enter. Click the table symbol that appears next to data S1. Specify the two power losses, each with weight 1. Click on Close to close the table. In this step, we will define the ambient temperature of the surroundings. The ambient temperature is defined on one point outside the model. This can then be used as reference for convection boundary conditions. Right-click in the model browser and choose Create. Then create a new load collector. Name the new collector as SPC temp and do not specify any card image. Click on Close to define this new load collector. From the View tab, extend the panels by clicking on Panels. Near the bottom right corner, select the Geometry page. Click the Nodes button and specify the X, Y, and Z coordinates in such a way that a node will be created 2 centimeters below the geometry. Once the coordinates are specified, you can click on Create and then click on Return. Make sure that SPC temp is the current load collector. Its name should be in bold characters. From the Analysis page, choose Constraints. The yellow field should show nodes. Select the newly created node graphically. Uncheck the box in front of DOF1 to DOF6 and verify that the entry fields are set to 0. The relative size should also be set to 10. Click the green Create Edit button. In the card image window that appears, type 25 in the field for D and then press the Enter key. Press the Return button to close this window and press the Return button again. Finally, save the model. In this step, we will define convection boundaries. To do this, we right-click in the model browser, click on Create and select Group. In the Create Group window, for name, enter Convection Group 1. Change the card image to convection. Then click on Unspecified next to MID, and for material, choose copper. Click on Slave Entity IDs to activate it and then on the elements in the yellow field. Turn the selectors at the bottom to add solid faces and elements. Then click Elements in the yellow field. Choose the button by collector. Check Patch and Ground and click Select. Click on Nodes in the yellow field. Select graphically 4 nodes on the top copper face representing patch and 4 nodes on the bottom copper face representing ground. Click on Add and you should see graphically that the selection has worked. Click on Return. The convection group 1 should show non-zero number of elements. And then click on Close. In this step, we will define convection boundary on FR4. The steps almost remain the same. We right-click in the model browser, click on Create, and then click on Group. In the Create Group window, for name, enter Convection Group 2. Change the card image to Convection. Then click on Unspecified next to MID, and for material, choose FR4. Click on Slave Entity IDs to activate it and then on Elements in the yellow field. Turn the selectors to add solid faces and elements and then click Elements in the yellow field. Choose the button by collector and click on Substrate and click Select. Click on the nodes in the yellow field. Select graphically 4 nodes on each of the 4 side faces of the substrate. Click on Add. You should see a graphical confirmation of the selection. Click Return. Convection Group 2 should show a non-zero number of elements. Click on Close and save the model. Please note that the top faces of the substrate remains to be done. Since it coincides with the copper patch, we have to do something extra to select only the top element faces around the patch. We will create a set that represents those element faces. In the bottom right area, in the analysis page, select Entity Sets. Provide a name and click on Elements in the yellow field. This time, choose by window. Check Exterior and Visible Only and create a window with 5 separate left mouse button clicks on the corners of the patch as shown. Click Select Entities. The selection is highlighted. Zoom in to verify if the required elements are highlighted. If not, you can individually select them. Select Create and click on Return. The new set is listed in the model browser under the Sets section. In the details, you can find that there are around 3,747 elements in our selection. In this step, we will define the final convection boundary on the top face. The steps remain the same as previous. Right-click in the model browser, click on Create and select Group. In the Create Group window, enter Convection Group 3 for name. Change the card image to convection. Click on Unspecified next to MID and choose FR4 for material. Click on Slave Entity IDs to activate it and then on Elements in the yellow field. Turn the selectors at the bottom to add solid faces and elements. Then click on Elements in the yellow field and choose the button by Sets. Once you do that, check the set you just created. Then click on Select. Click the nodes in the yellow field and select graphically 4 nodes on the top surface. Click on Add. Click on Return. Then you should see a non-zero number in slave entity IDs. Click on Close to finally define the last convection group. The next step is to link the convection boundaries to the ambient temperature. At this point, we have 3 groups of convection boundaries defined, but they have no link to the ambient temperature yet. To do this, we first make sure that the SPC temp is the current load collector. Otherwise, right-click and select Make Current. You can also search for options in HyperMesh X. We will use the card edit option, the one that you can search on the top right. You can use the card editor and click on Elements in the yellow field. Select By Group button and check the 3 convection groups and then click the Select button. Click in the space next to Config and select Slave 3. the type automatically changes to the one you see in the image. Click the green Edit button. On the card image window, click the yellow TA1 button and then select graphically the special node for the ambient temperature. The node number becomes visible under TA1. Click the red Return button and click Return again. Next, save the model. The next step is to create a load step. A load step is a simulation setup that specifies the analysis type, the loads, and the boundary conditions. Once again, in the model browser, right-click and choose Create. Select Load Step from the available options. For the analysis type, choose Heat Transfer Steady State. For load, choose total EM losses that we have defined with the load add card. For SPC, choose SPC temp. Now click on Close and then save the model. The final step is to run the simulation or the Optistruct solver. At the bottom right, choose the analysis page and click on the Optistruct button. Click Save As and confirm the name and location of the final FEM file, that is the solver deck. Click the green Optistruct button. This launches the simulation. The solution process takes only a couple of seconds to simulate. You should read analysis completed or Optistruct job completed. Next, we can click on results to look at the results in Hyperview. Once Hyperview opens up, we see that the model is loaded and we select components, click on all and click on apply to look at the contour plot. On the top left, we will see the scale of the temperature. We notice that the radiating copper patch can reach up to 75 degrees Celsius. This is how a user can perform thermal analysis by coupling Feko and Optistruct. Please reach out to us if you have any questions, and thank you for watching this video.